Hello. In this video, we'll be talking about how to solve problems where our goal is to assign geometry, hybridization, and function of each valence orbital at a specific atom in a molecule. And the example molecules I'm going to use are ammonia, aluminum trichloride, and CS2, the examples are listed here. With all of these, I will skip pretty quickly to the Lewis structure for each of these example molecules. These are good places to practice, so feel free to pause the video at A, B, and C and try to draw Lewis structures. I'll focus more on, once we have a Lewis structure, how do we determine the geometry of the central atom, how do we determine the hybridization of the central atom, and how do we assign function to each valence orbital of that central atom. So here we go. Let's start with A. Let's talk about ammonia. Feel free to take a pause here and draw the Lewis structure for yourself. When I draw ammonia, I get an N as the central atom and 3 H's. And in this problem, we're going to focus on the central atom, nitrogen. So the first question is, what's the geometry of that central atom? To figure this out, I count the number of atoms directly bonded to the central atom plus lone pairs. So it's really like the number of things that are attached to that central atom. The book calls this steric number, I believe. And so that's what we're counting here. And so I'm going to change colors, say, all right, so the number of atoms that are attached to the central nitrogen, well, there's an H attached directly to it, another H attached directly to it, and a third H attached directly to it. So that's 3. I'm also adding on the number of lone pairs. There's one more lone pair, so that's 4. So the steric number of this compound is 4. Once I know that the steric number is 4, that actually tells me the hybridization. The hybridization for a steric number equals 4 compound is sp3. And I forgot to write the geometry down here. The shape is tetrahedral. In terms of what this means, I'm going to actually draw that shape. Right? So what it means is that that central atom, we think about it as having 4 orbitals. If you haven't yet talked about this wedge and dash format, I imagine you will at some point. I'm just trying to represent these in the shape of a tetrahedron. There are 4 sp3 orbitals present at this nitrogen. Those are the valence orbitals that I want to assign to do part 3. So the question is, what is each of those valence orbitals doing? To answer this, I generally like to just say, all right, if I've got 4 of them, I'm just going to write, well, I've got sp3 orbital number 1, sp3 orbital number 2, sp3 orbital number 3, sp3 orbital number 4. I've got 4 orbitals I've got to assign. What are they all doing? And I know that I have, switch colors once more, I know that I have these bonds between N and H, these single bonds, these sigma bonds. Some of the valence orbitals of nitrogen must be involved in making those bonds. In this case, since there's only one type of orbital available, I'm pretty sure that I'm using 3 of those orbitals, capital N. I'm using 3 of those orbitals to make the sigma NH bond. Right? So what I'm saying is that the NH bond is made by taking the sp3 orbital at nitrogen and the s orbital at hydrogen and mixing them together. So the sp3 valence orbital at nitrogen is involved in that bond, is making a bond to hydrogen. There is one sp3 orbital left over because there's only 3 NH bonds. That last orbital must contain the lone pair because there's a lone pair and it needs a house, right? It needs a home. I tried to draw a second dot and it failed. There's the dot. The fourth sp3 orbital holds that lone pair. I have now assigned a function to each valence orbital, to the sp3 orbitals at nitrogen and NH3, and that completes the exercise. Pause for a second. We're going on to example number 2, AlCl3. I can do the same thing. I'm going to draw the Lewis structure of this. Feel free to pause and do that for yourself. There are lots more valence electrons to worry about in AlCl3. But this is the Lewis structure. Once again, we're going to start with steric number, which as defined above is to count the number of atoms directly bonded to aluminum plus the number of lone pairs. And in this case, I've got a Cl, a Cl, and a Cl, and no lone pairs. So the steric number is equal to 3. Compounds with steric number of 3 have a trigonal planar geometry. And so that's the geometry of this compound. Compounds with steric number of 3 have an sp2 hybridization. I'll talk a little bit about what it means to have an sp2 hybridization before we talk about kind of what's going on in aluminum. So if we have an sp2 hybridization, what that means is that the valence s and p orbitals, which for aluminum is the 3s and the 3p, are hybridizing. They are mixing together. And since it's sp2, that means that the s is mixing with 2 p's. Right, so the sp2 is actually telling me how many p's are getting involved. I'm going to mix those together. Anything that I didn't mix just gets spit out the other side. So I still have a 3p orbital left over. It's this one. Right, that one was not mixed, but the other 2 p's are going to mix with the s's. If I'm going to mix 3 orbitals together, I'm going to get out 3 new orbitals, and those new orbitals are going to have an energy somewhere in between the s and the p. There's going to be 3 of them, and these are going to be sp2 orbitals, so named because they come from mixing an s and 2 p's together. All right, so what does that mean? It means that the valence orbitals available at aluminum are those orbitals that we just defined. It's 3 sp2 orbitals plus a p orbital. You may the shape of those, so as a simplified shape, the 3 sp2 orbitals exist in a trigonal planar arrangement. And the p is perpendicular to that trigonal plane. But these are the 4 orbitals I need to assign, like regardless of all of that. Like the 4 orbitals that I need to assign function to are 3 sp2s. This is now going to answer question 3, what is the orbital function? And a p. What are these various orbitals doing? Well, the hybrid orbitals generally are involved in making sigma bonds if there are sigma bonds to be made. I need to have 3 AlCl bonds, right? I need 3 sigma bonds, and I've got 3 sp2 orbitals. So that's handy and dandy. Probably each of these is making one of the Cl bonds. Right, so basically showing like, oh yeah, the Cl's are going to be arranged in that trigonal plane. They're going to be sigma bonded. The p orbital is present, and it has a function. In this case, there's no additional electrons, right? There's no lone pair at that aluminum. So that p orbital is simply empty. Like its function is to be empty. When you move on in chemistry, you'll see that actually empty orbitals are really useful to think about because they kind of tell us where the next electrons are going to go. Okay, so that walks us through assigning geometry, hybridization, and orbital function to aluminum in aluminum trichloride. Finally, let's talk about example C, CS2. Again, you can take a moment to draw the Lewis structure for yourself. When I draw it, I get C with double bonds to S, and lone pairs at the S. There we are. All right, in this case, steric number, the number of atoms directly bonded to carbon is 2. There's sulfur number 1 and sulfur number 2. And there are no additional lone pairs at carbon. This results in a linear geometry. Point 2, when I have a linear geometry, that gives me sp hybridization. That gives me sp hybridization. I'm going to do the same exercise that I did up there just because it might be helpful. If I'm going to have an sp hybridization at carbon, and just to be clear, I'm focusing on the central atom when I do this analysis, I can have my 2s and my 2p valence orbitals. They're going to mix together. In this case, though, I'm going to mix not an s with 2 p's like I did above, but just an s with 1 p. And that is going to get me to, I'm going to have 2 2p orbitals left over, and I'm going to have 2 sp orbitals formed by mixing the s and the p. I get out 2 hybrid, 2 mixed orbitals. Those are the orbitals present at carbon that I need to worry about. And so I can draw. So what does that look like? Well, the 2 sp orbitals are in a linear arrangement. They're 180 degrees from one another. The p orbitals that are left over, I'm going to actually kind of remark these in red. The p orbitals are perpendicular to those sp orbitals and perpendicular to each other. It's a little tricky to draw, but one of those p orbitals is straight up and down. The other one is going directly back into my screen and directly out of my screen. So I'm going to draw it this way. Right, it's turned on its side. It's 90 degrees. Rotated 90 degrees from the first p orbital. That's the arrangement of the valence orbitals at that carbon. The 4 valence orbitals I need to worry about here are sp, sp, p, and p. What are they doing in this case? Well, in this case, I've got 2 sulfurs that are bonded to carbon. And in this case, they're attached to carbon via a double bond. And so the key thing is that I need to find a way to make two bonds between carbon and sulfur, right? I need to worry about bond A and B. Another way of saying that is I need to worry about the sigma bond and the pi bond, the first bond and the double bond. So to make those sigma bonds, generally the default is to use the hybridized orbitals. And so in this case, like I'm using one sp orbital, this one, to make a sigma between carbon and sulfur, and I'm using the other sp to make a sigma bond between the other sulfur and carbon. So that's the function there. The second bond, the pi bond, must be formed using the other orbitals. And pi bonds, as you may recall, are generally formed by overlapping p orbitals that approach each other in a parallel fashion rather than in a head-on fashion. And so the orbitals involved in making those double bonds are the p orbitals. Where essentially there's going to be a p orbital at sulfur as well that can overlap with the p orbital at carbon to make one of those pi bonds, and there's going to be a p orbital at this other sulfur which can overlap, I'll make it green, which can overlap with that p orbital to make the other pi bond. And that is all I got.